This poster describes understanding mass as relational counterforce from nucleostatic, strong nuclear force, field at Bohr over edge to the 3/4 power for a Pauli electron nucleon electron at 8/7 the distance. Now, electrostatic force and this extra 1 over r have an inner reaction. Notice there's two of these always going. And so in fact, what happens is you get these factors with a sub o over r sub e to the 3/4 power. This you can see in things like the electrostatic constant, or you can see this called alpha, or 1 over alpha fine structure constant. So that means the electrostatic field, though, is a cubed for electrostatic, but for the extra 1 over r, which I believe is strong nuclear force, is to the 4th power. Now that means that when you're trying to interrelate them, that means those two distances are relative exponents. So when you're comparing one layer to the other, you get from the potential to the electrostatic, you get that 18,788 r sub e over a sub o over r sub e to the square root, which is the 137 that we all know as the fine structure constant. What I'm introducing here is that there's another one, and it's that same 18,778 ratio of the distance of the Bohr radius, or the standard 1 electron, 1 neutron equilibrium versus the particle edge. You have to upscale within that field to get from Bohr at Planck at Bohr to Planck at the particle edge, which is what we call charge. And that ratio is 1,604.2. You say, well, that's not the right number. Well, we're missing the scaling factor because these systems have 2 electrons, which push out those fields a little bit further than the Bohr radius. Now, understand that it also includes the number of nucleons, and there's more complexity to this, but I'm doing a very simplified 2 electron as if 2 proton system. I know it's not real. That would mean that you would not have the nucleostatic electron-electron. It only applies when at least one of the particles is a physics color particle. So as a result, you get 1 over 1 cubed minus 1 over 2 cubed. And that's 1 minus 1/8, which is 7/8, and thereby 8 over 7, or this extra factor of 1.142856. Now what happens to that 1604? You see, if you take just the scaling of 3/4 power of the fine structure constant, the equilibrium over edge, distances. So as a field ratio, distance over distance being a dimensionless. But then you add that it has to be a Pauli pair set, you get 1.833. Now I was almost there, but then I remembered that we had to get the anomalous moment. And that is, we have to add in that the particles have distance. And when you do that, I get to 1 to 1836.18, which is a very close mass to the experimental value of the ratio of the mass of an electron versus the mass of a proton. So please understand, this 1 over extra r is what Bohr said, but we all know it's not a gravitational orbit. Although we still use the name orbital and we still use the name angular momentum. In fact, a 1 over extra r is just a very simple Planck, okay, obviously divided by the mass over that. So as a result, I also can get the G in terms of just Planck and these scaling factors. So there it is, there's a calculation. So my conclusions are that we need to approach mass as positions and fields, but for multiple interaction types, okay? Strong, weak, okay? Electrostatic, and also understand the multiparticle set that defines them. And when we do that, we will actually be able to define gravity and mass based upon Planck, thereby it being fully derivative of electrostatic forces and not a separate force, which is pretty important.